Okay, so welcome. I'm Maciej, and I'm going to present some of our recent results on hardware-accelerated graph mining. Graph mining is a part of the graph processing landscape in which we care about solving complex problems on graph datasets, for example, listing k-Cliques or enumerating some other complex graph patterns. Graph mining has been used in a lot of different computational domains, for example, biology, chemistry, and many others. Let's take a look at what are the challenges in today's graph mining. As an example, let's consider the established Bron-Kerbosch algorithm, a solution for maximal clique listing. We're not going to take a look at the details of this algorithm, but what is really important to realize is that this is a complex algorithm. As we can see, it has a deeply recursive structure. It doesn't have the notion of iterations that we know, for example, from simpler schemes such as PageRank. Thus, it has non-straightforward parallelism, complex memory access patterns, and many other issues. As a comparison point, let's take a look at PageRank. In PageRank, all we have to do is to iterate over all the vertices and send updates to our from every vertex. We send some updates to our neighbors, and then we gather the updates from the neighbors. PageRank is used to, for example, rank websites. Now this means that we grab some part of the graph, we have our part of the graph, and we can see our vertices, our edges. We run this thing in parallel, and we are basically gathering the updates from our neighbors, and we are sending the updates to these neighbors. And this is all we have to do, modularly repeating this a couple of times. Right, so this is not very complicated, and the point is that this is not what we have in graph mining. It's much more complex than that. Then many of these algorithms are computationally hard, and also we have not just clique enumeration and Bron-Kerbosch, but many other problems and schemes for solving these problems that come with similar challenges. Finally, our hardware is getting more complicated, not in terms of being massively parallel, but also quite heterogeneous. So what we really want is a paradigm that will enable high-performance graph mining algorithms that is on one hand general. So we want this paradigm to be applicable to many problems. We want also to have some guarantees on some theoretical guarantees on low work to have guarantees also on the resulting performance of these algorithms. At the same time, we also want it to be able to easily harness the potential, the power of this diverse hardware. Before we proceed, let's take a look at what hardware we mean exactly. Right, so we have many of these different architectures, and what we are going to focus on in this work is processing in memory. We are going to focus both on the variant called processing using memory, in which we are conducting some simple operations directly inside DRAM banks. But also we are going to take a look at how we can harness the power of processing near memory, PNM, where we have our compute capabilities outside DRAM banks, but very close to them. Now, why PIM? We decided on using PIM because on one hand, it's a very promising tool to tackle memory bottlenecks. That was illustrated in numerous past works. On the other hand, it's quite well understood, while still being something that has a lot of undiscovered potential. And finally, it's also been used successfully for speeding up simple graph algorithms such as PageRank, and we would like to actually take a look at how this can fare in the context of complex graph mining. So with this PIM architectures, we want to use it as a use case for our paradigm. So the ultimate outcome of our work is something we call SISA, which is a set-centric ISA. It sounds a bit mysterious, so let us take a look at this in a bit more detail. So the fundamental part of SISA is the so-called set algebraic view of graph mining algorithms. So in this set algebraic view, we are looking at graph mining algorithms through the perspective of set algebra building blocks. So we are trying to isolate fundamental building blocks in these algorithms, namely sets, and such as sets of vertices you can see here. So we can see two vertices, U and V, and they have their neighborhoods, which we can treat as sets of these vertices. And also set operations, such as set intersection, that you can see here marked with this dashed line. But then the other part is to implement these set algebra building blocks with an accelerators with PIM architectures. As we will see, this on one hand enables wide applicability, so we are able to we provide more than 15 algorithmic formulations that are based on these set algebra building blocks. On the other hand, it comes with simplicity and easiness of reasoning, because all we have to do is to apply these fundamental building blocks, and there are not that many of them. And finally, it comes with a lot of performance, so we will see we have up to almost order of magnitude speed up for some complex graph mining problems. Let's take a look at this in the context of some simple example. So here we are going to consider the triangle counting, which is the algorithm in which we want to count all the triangles in our graph. And now in one part of the whole design that we provide is set-centric algorithms and formulations, right? So we can see here there's a triangle counting algorithm. Again, the details are not important. What is important is that many of these operations in this algorithmic code are going to be mapped to some SISA set-centric instructions. And the most important one that we focus on here is the set intersection. So in triangle counting, we have a double loop. We iterate first over all the vertices, then we iterate over the neighbors of every vertex, and then we are intersecting these the neighborhood of the first vertex with the neighborhood of the second vertex, and that's our crucial set algebra building block for this specific algorithm. Then what we are doing, we are mapping these operations to the set algorithmic implementations that are being implemented, possibly in software, possibly in hardware. But then the final part, which is the most important for the speedups, is really mapping these things down to the acceleration and hardware through PIM. So we can see lots of details here. We'll take a look at these details a bit more thoroughly a bit later. So to summarize, we provide on one hand set-centric paradigm and formulations of algorithms that on one hand are applicable to many graph mining algorithms and also come with guarantees for theoretical efficiency. On the other hand, these formulations are then implemented with set algebra building blocks and with set-centric ISA that offers high performance set organization. So on one hand, we provide representations of set, and on the other hand, we provide different variants of the algorithms for the execution of these set operations. And then there is the actual way that this is done in hardware using PIM. So let's start with the first part, with the paradigm and formulations. Again, let's consider Bron-Kerbosch. So the essence is really to decompose a given graph mining algorithm, for example, the Bron-Kerbosch algorithm, into set algebra building blocks. And what is really cool is that, as we can see already from this listing, there are many of these operations visible in Bron-Kerbosch. So the nice thing is that this is not limited to Bron-Kerbosch, but also to many other algorithms. So we are able to develop or simply re-express algorithms solving more than 15 graph mining problems using these set algebra building blocks. On the other hand, as we only have a few of these operations, the way we are going to speed up the algorithm, for example, by playing with different variants of set intersection or set union, is going to be simpler than dealing with all this complexity of the whole algorithm like as a whole at the same time. And finally, we can also get more performance because on one hand, we can tune these different set build implementations of these different set algebra building blocks with different variants of set operations. And you can select for a given scenario which one the variant is the most beneficial one. We analyze the expressiveness of our set algebra based paradigm, comparing this to other paradigms. So here in this table, you can see a couple of different things. So in this leftmost column, you can see different abstractions or programming models for graph analytics. So we compared the set-centric paradigm to vertex-centric paradigm, to edge-centric paradigm, and to other popular abstractions used for programming graph algorithms. And on the first row, we can see different aspects that we are considering. So an example scheme and whether there is an underlying algebra, what is the key element and the key operations of a given paradigm, and then something which is most important for us in this slide are the supported problems. So we consider on one hand support for pattern matching problems in graph mining, such as maximal clique, k-Cliques, then subgraphs and subgraph isomorphism. We also consider different learning schemes, such as link prediction, clustering, vertex similarity, and others. And then also we consider simpler algorithms, such as the ones that were heavily researched in the past, namely triangle counting, BFS, connected components, and PageRank schemes. And here we can see whether a given paradigm supports a given graph algorithm problem. The full support is indicated with the full battery symbol, and the partial support is indicated with the half battery symbol. What we can see is that the set-centric paradigm proposed in our work supports, unlike all these other paradigms, supports fully the graph mining problems, but it's lacking in the low complexity scheme. So we are not really going to target simple algorithms, like low complexity algorithms such as BFS or PageRank. And by low complexity, I mean the computational complexity. The key element in our paradigm is, of course, sets of vertices and edges, and the operations are set operations. Now, if we compare this, for example, to the vertex-centric paradigm, you can see that the key element there is a vertex and its neighbors, and the key operation is a vertex kernel that we program. And for example, another paradigm, which is also based on algebra, but linear algebra, it's Graph Plus. The key elements there are matrices and vectors, and the key operations are operations on these actions or on these elements. We provide many more set-centric formulations. You can check all these things in the paper. Now let's move to the part number 2, to how these algorithmic formulations are going to be implemented in the context of how do we implement these set representations and these set algorithms executing all these operations. So if we consider some example graph with 16 vertices, an example set of vertices can be this, some set containing 5 vertices. Now we can represent this set using, for example, a sparse array, where we explicitly store all these vertices as explicit numbers contiguously in memory. Or we can also represent this as a dense bit vector, where we store this set as a bit vector with n bits, and now bit set to 1 indicates that a given ith vertex with the ith index is present in a given set, while 0 means that a given vertex is not in a given set. Right? And now in SISA we support both of these representations. But what is more interesting is that we can now, depending on these representations and even some other aspects, we can now run different variants of the set algorithm. Right? So let's say that we want to intersect 2 sets, that we want to run the set intersection. Now, depending on how we present these input sets, we may want to execute different variants of a set intersection algorithm. Right? So for example, to intersect 2 sparse arrays, we are going to use different variants rather than whether we want to execute intersection of a sparse array and a dense bit vector, or whether we want to intersect 2 dense bit vectors. And in SISA specifically, we are going to use the SISA PNM, processing near memory, for executing intersection or other set operations that is at least one of the input sets is stored as a sparse array. And then we are going to use processing inside DRAM for intersecting 2 dense bit vectors. But we can go even more towards even more fine-grained decisions. So for example, depending on the sizes of these sparse arrays that we are going to intersect, we can execute these different variants of the specific set algorithm for intersection. So on one hand, if we are intersecting 2 similar sized sparse arrays, we prefer the merge intersection, where we simply iterate through 2 input sets which are sorted, and we identify simply common elements as we go. And the complexity of this thing is going to be n plus m, where n and m are 2 different are the sizes of the input sets. While if we want to intersect 2 sparse arrays that have the sizes of which vary a lot, we prefer a different variant called galloping, where we iterate over the elements of the smaller set, and then we use a binary search to find a specific element from like 1 by 1 from the smaller set inside the sorted bigger set. And the complexity of the scheme is m log n, where in this case m is the size of the smaller set and n is the size of the bigger set. Right? And again, in SISA we offer all these variants. And yes, it does look a bit complicated, but now let's take a look at how we simplify this through automatic execution inside hardware. So yes, now let's move to the final part, to the hardware implementation of SISA. So it looks, so this diagram looks a bit complicated. So let me maybe go through all these elements one by one. So the green blocks are blocks which are related to SISA, or proposed in SISA as some sort of extensions. So what the general overview is that we issue our instructions to modify some data in the memory, and now if these instructions are related to the set operations that we are implementing here, these operations will be intercepted by a small controller that we call SCU, and this controller is going to decide what variants of set operations and how are these variants are going to be executed inside using our PIM acceleration. Right, so while executing event set operation, the SCU is going to select the best set operation variant, and in this process is going to use the additional information about the sets called the metadata of SISA sets that we store in memory, and we will also cache in a small cache attached to SCU. Now, one way of the selection that we are going to execute, we're going to conduct in SCU, is what is the set representation of given two sets, right? So in this part, the SCU is going to select whether we execute, for example, the intersection of two sparse arrays using SISA PNM, or the intersection of two dense bitmaps using the SISA SISA inside memory execution. On the other hand, we also, in this moment, consider the set algorithm variant to be selected, right? So now, depending on the size of these input sets, the SCU will either execute the galloping or the merge-based intersection. And these decisions are guided by our performance models. So you can check details in the paper, but we provide performance models based on the fact that the merge-based intersection and other set operations are going to be mostly streaming related, while galloping operations are going to mostly are dominated by random memory accesses. And based on this, we provide the estimation of the runtimes of these operations and help the SCU with the right decisions for where to run these operations. In our evaluation, we want to, one hand, we want to show that SISA enables accelerating the state of the art, and our main baselines that we want to compare is, on one hand, variants which we call non-set. So these are state-of-the-art implementations that don't use or may use set operations, but they are not really specifically focusing on using set operations. Then we compare this to the set-based baseline, which is really just set-centric paradigm we propose with standard hardware underneath. And the third baseline is SISA, which is the combination of the set-centric paradigm and with the PIM acceleration. So this way we can also illustrate what are the main gains in performance, whether we are having these performance improvements by using just set operations, or also whether what is the fraction of SISA acceleration from PIM. We use the established infrastructure for the simulations, and the considered platforms are our hardware proposed extensions for SISA, and for anything else, we use a high-performance out-of-order many-core CPUs. We use the same parameterization as in the past, and for fairness, all the baselines use bandwidth scalability. We use many different problems, mostly related to mining complex patterns or to graph learning schemes such as vertex similarity, and we compare graphs coming from different domains, for example, from biology, social sciences, brain studies, web analysis, and economical or structural networks. Here we can see the results for pattern matching. So in pattern matching, we first pick the clustering scheme, which is using the Jaccard-based coefficients, and on this x-axis of this plot, we can see different graph datasets. On the y-axis, we can see runtime in millions of cycles, and bars of different colors correspond to different baselines. So here we have, again, this non-set variant, the set-based, and the SISA. We compare the non-set implementation coming from a highly optimized gap benchmark suite. And the complexity of this scheme, of this clustering scheme, is O of n to 3. And here we also plot the overall summarized SISA speedups over the non-set variant and the set-based variant. What we can see here is that although SISA is the fastest out of all these baselines, the non-set variant is actually the second fastest, and it outperforms the set-based scheme. So in this example, we can see that that using SISA helps a lot, but just using set formulations is not really getting us too much performance. And that's really because we compare to a really optimized implementation coming from the GAP suite, and also from the fact that this clustering scheme is actually having quite low computational complexity. And but if we move to some more complex pattern matching problems, such as k-Cliques, here we already see that the pattern is somewhat different. So again, we can see on the x-axis the graphs, on the y we can see the runtime in millions of cycles. But this time, what is clear is that on one hand, SISA outperforms by a large fraction the non-set variant, but also the speedups over set-based are there, and they are smaller than the first one, which means that that our paradigm gives us more performance, still being the second one, because the hardware acceleration pushes the performance even more far away. But using the sets themselves are actually going to help here for the problem of k-Cliques. And finally, we also have the very computationally hard problem of maximal cliques listing, which is coming from a given very high complexity. And here we can see that the cutoff that we are using to basically eliminate runtimes which are too long is showing us that really non-set is not really finishing within the time frame that we have here, and SISA is again having consistently, well, in almost all the cases, the highest performance, but again really outperforming this simple set-based thing that is not using hardware acceleration, PIM acceleration. And all these speedups, all these gains are really mostly to the fact that we have this, that we not only have this PIM acceleration, but really also we have this automatic decisions on which variant of these set operations to select, and which set representation is the most advantageous for a given set. In the paper, we provide more analysis, both empirical ones and theoretical complexity analysis, as well as a detailed investigation on different architectural features of both SISA and related work. Thank you for your attention. I will now take any questions.